of Module 5, Heap Sort Part 2. This will be the last part of Module 5. I want to make Module 5 shorter. In this way, you will only prepare for your final on 2 modules, Module 4 and Module 5. Module 6, I will not include it in the final. I just give you a quiz on Module 6, so you have a chance to improve your quiz grade. Remember, we will drop the lowest 2 scores of 6 quizzes. Yeah. But for the final, you only need to focus on Module 4 and 5. Yeah. And I make the Module 5 shorter, so then it will be easier for you for prepare for the final. Yeah. All right, so let's start. Oh, and for your homework assignment number 2, the last 3 or 4 questions, you need this part. Yeah. So you need some formula from this part to complete those questions. All right, so let's start. B.1, heap nodes in each level. Yeah. All right, so let's look at that. Because each level, let's look at from the bottom level. Then we go higher, level by level, higher. All right, first, let's look at the number of leaves in a heap. Yeah. We want to find a formula to calculate that number. Yeah. First, we want to describe leaves. How do you know a node is a leaf or not? Right? You need to find that information first. Yeah. So let's look at a general heap structure. Yeah. So when you look at this graph, you can see what are those nodes that are leaves. So very easy. These nodes, 3 here, 2 here, they do not have any child node. So they are leaf nodes. Yeah. All right. So from the picture, from the graph, we can see what are leaves. But how do we use formula to check if a node is a leaf or not? Right? Yeah. So we want to find that information. The first observation, we can see nodes without children. What are the leaf nodes? Nodes without children. Yeah. So that description can give us some important information. Yeah. So look at the parent-child relationship. Okay. Yeah. If the parent corresponds to the element A of I, array element with index I, what is the child node? Child, we have left child and a right child, right? Yeah, but here we use the left child, left. Yeah. Why we use left child here? The reason is very simple. If a node has a child node, it must have a left child node. But for the right child, sometimes that node may have, sometimes it may not have. If a node is not a leaf, it always has a left child node. Yeah. For that reason, so we choose the left child, not right child here. Okay. All right. So now, next question. How do we know if this left child node exists or not? How do we know that? Right? Yeah. So given the index, for example, given index I, how do you know it has a left child or not? Can you find a simple formula for it? Yeah. So the conclusion is very simple. Yeah. If the index 2i is out of bound, then it has no left child. Out of bound, the bound, right? The bound for array indices. Out of the array bound, yeah, no such child node. That simple. Yeah. So let's use the formula to represent this relationship. Okay. No child. Yeah. The condition is this. I less than or equal to n. Yeah. I, its parent index is within the bound. Parent node is within the bound, right? So we imagine some possible parent node within the bound, but left child index is out of bound, greater than n. That's out of bound, right? So remember the index range for a heap. We do not use the 0. Remember, no nodes corresponds to the 0 index. Yeah. Remember from the part of A, we make this assumption. Otherwise, the parent-child relationship does not work. Okay, does not work. So we exclude that special node. Other than that, the remaining nodes from 1 through n, number of nodes in the heap, that's the range. Okay, so the range is this one. But out of bound, 2i greater than n, out of bound. Yeah. So with this inequality, yeah, so we can simplify it, divided by 2 for the right half of inequality, n over 2 less than I. Okay? Yeah. So that's the newer version of inequality. Okay? All right. So next, we want to find the smallest such I. Now, given this inequality, we want to find which index satisfies this inequality, but it is the smallest. Okay, yeah. So the answer is, look at this. Yeah. Remember, this is a strictly less than. Strictly less than. Okay, not less than equal. Strictly less than. So we take this expression. Floor function of n over 2 plus 1. Because if n is an even number, we need the I greater than this half of even number. So plus 1. So that is the smallest such index. So with this analysis, now we can get the answer, or we can get the range of indices that those nodes do not have child nodes. This is the range. Okay? I must be in this range. Lowest bound, highest bound. Okay? All right. So with this range, can you figure out how many i's fall in this range? Can you figure that out? We need a formula to write that expression. Okay? The answer is this. N minus floor function of n over 2. Remember, minus not this plus 1. Do not minus this 1, okay? Minus the integer 1 less than this lower bound. Because this lower bound is still included in I. We don't want to count this lower bound, when we do subtraction, okay? We don't want to subtract this lower bound, right? So we subtract the number before this lower bound. So that's why we do not have that minus another one. Don't minus that, okay? So this is the formula. The number of elements, the number of indices in this range. Okay, all right. And this formula could be written in another format. The seeding function of n over 2. Same. Yeah, different expressions, but the values are the same. Why? Here I give you reference of the formula. Yeah. Floor function of n over 2 plus seeding function of n over 2 equals n. So you can find this formula in our textbook, page 477. Yeah. And we can prove easily if you want to prove it. Yeah. It's not very hard. You can prove it. Yeah. Look at even number, odd number, two cases. So you can easily prove this formula. Yeah. Now we just use it so we can write in a different version. Why we need to write different version? In our B.2 video, you will see sometimes we need to use this version. Okay? Sometimes we need to use this version. So that's why we may want to have a different version. But, the first version also, in many situations, we need to use the first version. Yeah. All right. So we finish the bottom level, the leaf level. Next, we want to go one level higher. Okay? One level higher. All right. So the next topic, number of internal nodes with height 1. So here you can see there are two concepts. First, internal nodes. Second, height of each node. There is a height number. Okay? First, internal nodes. The terminology, leaf nodes, we call external nodes. So all the leaf nodes, sometimes people just call external nodes. Okay? Then non-leaf nodes, the remaining non-leaf nodes. Okay? Yeah. All non-leaf nodes, we just call internal node. Yeah. So that's simple. Yeah. So we want to look at internal nodes. Each internal node must have a child. Must have at least one child, right? Otherwise, it will be a leaf node. Yeah. All right, so let's look at this diagram. Yeah. First, I also want to explain this height. Yeah. Because many times, many students feel quite confusing on this concept, height concept. Yeah. Actually, the height concept will pretty follow our intuition. Use our intuition to understand this height concept. All right, first look at the node of this one. What is the height? What is the height? Yeah. So first, you need to have a reference line or plane. Yeah, reference, because the height is how high it is with respect to the reference, the ground level reference. Yeah. So this is the ground level. Okay? Yeah. This is also ground level. Okay? Yeah. 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 Okay? All right. So the nodes, leaf nodes, all the leaf nodes are on the ground level. Okay? Leaf nodes are on the ground level, so their height is 0. Leaf nodes, they have height 0. Also here, height is 0. No height. Okay? So that matches our intuition, right? Something on the ground, there is no height, right? If there is a non-zero height, it must be above the ground. Okay? Above the ground, all right? Yeah. So based on this intuition, now you can see these nodes, they have height 1. Okay? One level above the ground. Okay? One level. How do you count level? The number of edges. So this is edge. Okay? From parent to child. So there is an edge. So if there is an edge in the path, yeah. So you start from one node, you going down, get to a leaf node. There is a path, right? Along that path, how many edges? That number of edges corresponds to the height number. Okay, so that's simple. Follow our intuition. Yeah, match our intuition. So 1 here, also 1, height 1. Here, the ground level here, right? So height 1. Okay, all right. Then let's look at the root node. What is the height of the root node? Okay? Also, yeah, because you may argue from root node, we can go down from one of the leaves this way and also go down from a path that way. Which path do you use to count as the high number? The longest path. Remember this, the longest path. This path, 3 edges, 3. That path, 2 edges. So we will take the 3-edge path, not 2-edge path. So in this way, the root node has height 3. That's the concept. That's the height concept. Okay. Yeah. So you need this understanding to solve the last few questions in homework assignment number 2. Yeah. All right. So now let's go to the next step. Find the answer, find the formula on number of internal nodes, or we know nodes with height greater than 0 must be internal, right? So sometimes we can ignore this internal. So we don't need, emphasize that. Okay, sometimes, yeah. So number of nodes with height 1, yeah. All right. So let's do step by step. First, let's look at the number of all internal nodes in a heap. Yeah. So that's easy. Yeah. We start with total nodes in a heap, n. Yeah. Next, number of leaves. We found it, the formula n minus flow function of n over 2. Yeah. Next, number of internal nodes. Subtraction, the difference of the last 2 numbers. Okay, so the difference is flow function of n over 2, number of internal nodes. Yeah. That means the nodes with height greater than 0. All nodes with height greater than 0. Yeah, this number. Okay, yeah. Number of internal nodes with height 1, another level forward. Yeah. To do this, we just use the similar way we used in the previous slide. Yeah, similar way. Yeah. Okay. What are those? Now, we want to describe all the nodes satisfy that requirement. How do we describe it? Okay. Their children are leaves, right? Height 1 nodes, all the height 1 nodes, they have this property. Their child nodes must be leaf nodes. Yeah. And we know how to describe leaf nodes, right? Yeah. Here is the description. The child node, we use left child. We still, 2i, we still use the left child representation. 2i. 2i must be in the range for the leaf nodes. This is the range for the leaf nodes. Right? Yeah. So we put there. Then that gives us the range for the I. The range for indices that correspond to nodes with height 1. That's simple. Okay? Yeah. So we can divide it by 2, so we get this formula. Okay? So the right half, this part, easy to understand, right? Divided by 2, then take flow function. But how do you see the left-hand side, right? Left-hand side, divided by 2, take ceiling function. Yeah, we need to get the upper bound, right? Divided by 2, take the ceiling function, okay? Yeah. But how do you get this expression? Not that straightforward, right? Yeah. Here, let me give you a formula. Yeah. Here, we need to use a simplification formula, this formula, okay? So you take a 1/2 flow function of n over 2 plus half, yeah, because this one divided by 2 plus half, right? Then you take the ceiling function. Okay. Then this expression can be simplified to this expression. Okay? And we put this expression here. Okay? Yeah. But you may ask me, how do you get that, right? You may ask me, how do you get that? You cannot find this formula in our textbook. You cannot. Okay? Yeah. But we can prove it. We can prove it. Yeah. If you really want to try, prove it. I can tell you the idea, how to prove it. Yeah. All right. The denominator here is 4, right? Yeah. And you consider n equals 4k plus some remainder. The remainder r could be 0, 1, 2, 3. 4 cases. Yeah. So you need to discuss 4 cases that verify for each case it is true. When r equals 0, is it true? Left-hand side, right-hand side, you compare. Okay? Simplify, then compare. When r equals 1, left-hand side, right-hand side, true or not, right? You go through all 4 cases. If all 4 cases true, then the whole formula is true. That's the verification steps. Yeah. Here I do not do that. Yeah. If you are interested in that verification, you can try. Yeah. All right, so here we just use this formula. Okay, so we get the range for the nodes with height 1. Okay, now it's the time to get the answer. What is the answer? Pretty straightforward, right? Just using the same way we did in the previous slide. Upper bound minus previous number of the lower bound. Not lower bound. Do not write lower bound. Then if you write lower bound, that's too much. Okay? Yeah. The number right before the lower bound. Right before the lower bound. Okay? Yeah. The previous, immediate previous number before the lower bound. Okay? Yeah. So the answer is this formula. Floor function of n over 2 minus floor function of n over 4 to square. That's the formula. Okay? Yeah. That's the height 1 nodes formula. Okay? Yeah. Here I may like to point out another one, but here it's not equal. Okay? Yeah. In our number of leaves, we have that equal case. Okay? Yeah, seeding function of n over 2. But here, be careful. This number is not equal, less than or equal. Because there is some special case. This expression is 1 more than that expression. There are some special cases. Yeah. So here I want to emphasize that. Yeah. The reason we also write this way, because later in the next video you will see we need this formula. We need this expression. Yeah. Inequality is fine for us. No, we don't need equality. Inequality is good enough for our estimation. Yeah. All right, so here I point this out. Yeah. Then the last step. Here we just complete height 1 formula. The remaining we want to know general height h formula, right? If we have the general height h formula, we can calculate the number of nodes with height 2, with height 3, with height 4, right? Remember our homework assignment question, you need to find the number of nodes with height 2. Okay? But the next slide, we just look at the general case. Then, any high number, you can do the calculation using that general formula. Now, so let's go to that slide. Okay? Number of internal nodes with any height, height h. Yeah. All right. So now we want to generalize the previous result. The generalization is pretty straightforward. Yeah. Yeah. The formula also quite straightforward. Yeah. Number of leaves, this formula, right? Yeah. Height 0 formula. Okay? Next one, height 1 formula. We just derive it. Yeah. So range is this. The formula, number of nodes formula is this. Okay? Yeah. can you see some pattern, some rule, common rule between those expressions, right? Yeah, I think you can see it easily, right? Yeah, all right. Now, the number of nodes with height, general height h. Yeah, based on that observation. Or then you can, if you like, you can do rigorous analysis using mathematical induction, if you like, right? Yeah, so here we do not use the mathematical induction. Yeah, we just do based on our observation. Yeah, the range for the height h nodes, h plus 1. Okay, yeah, because here 2, 1 plus 1, right? Yeah, yeah, and here h, n over 2 to the h. Yeah, 1, 2 to the first. Okay, yeah. So the range is this. Then the number of nodes, this is the number of nodes. Okay, so now you can see, yeah, this is our general formula. Okay, so if you want to calculate the number of nodes with height 2, yeah, h equals 2. Okay, number of nodes with height 3, you can use h equals 3. Okay, plug in into that formula. You just get the answer. That simple. Okay, yeah. All right, so that's all we need for B.2. Yeah. In the next video, B.2, we need to estimate how much is the cost to build a heap. Yeah. All right, so let me stop here. Yeah.